right, welcome back. We're going to talk a little bit more today about phase changes. We did a review worksheet earlier in your last lesson, but from your answers I can tell that we probably should go over this stuff again. So we're gonna start our last section of alloys, and it's going to be about phase diagrams, but we're going to focus today, we're going to talk about phase changes themselves and do some review for that. So what is a phase change? Well, before we talk about phase changes, maybe we should talk about what is a phase. We've talked about, you've always used states of matter. What about phase of matter? Phase of matter is when the material has its own structure and or composition. And that's where that structure really comes into play when we talk about solid, liquid, and gas, because that is how the atoms are related to each other. So solid has a nice structure where there's not much movement happening. Then you have your liquid where you have more movement, atoms can move around each other, and then of course gas, they fill up the container, they can go wherever they like. But don't forget that it also could be what that crystal structure is. Okay, so a BCC is a phase compared to an FCC. Okay, so a phase change would be a change of state or crystalline structure. And that's takes us back to that idea of the iron wire demo. If you guys remember this graph from looking at that, that iron, when heated to a couple temperatures, will actually change phase or its structure from around 900 degrees Celsius to just over 1300 degrees Celsius. It'll go from a BCC to an FCC. And once it gets much hotter, it'll go back to that BCC. So let's go remind ourselves, phase change is also a change, and could also be a change in crystalline structure. Now, atoms will form crystal structures that are the least amount of energy that is needed to become more stable. It's always why we do it. So when we're talking about those movement from BCC to FCC, where we talked about how the spacing would allow the metal to expand in a way that was more stable for the bonds between the atoms. So this was allowing for expansion with that heat happening. Because heat is really involved in this the entire time. Heat is the amount of kinetic energy, the amount of movement that is in a material the entire time, the total amount of kinetic energy. When we have the particles becoming more tightly packed, it means that we're losing energy, that kinetic energy is moving away from it, and that the atoms are becoming able to become closer together. When we have particles less closely packed, so we're moving toward a different crystal structure or even toward liquid or gas, it's because energy is being absorbed and each atom has more kinetic energy and it's moving around a lot more. Temperature is what we use to measure the heat of a substance. So temperature is the average kinetic energy of a material. Something can have a lot of heat, but if there's a lot of that object, then it's not going to have a very high temperature. But when we're talking about phase changes, the temperature, because so much energy is needed to change that phase from one to another, when we have a phase change, temperatures don't change. They will remain constant for the time being that is needed to get it from one phase change into another. So let's talk about that with our phase diagrams. So the first thing we're going to talk about is we're going to look at the phase diagram of a pure substance. A pure substance means it's not a mixture. In other words, we have an element or a compound. Compound means that they are always the same, like H2O, carbon dioxide, that sort of thing. Okay? When we have a pure substance, they have a melting point. It is a specific temperature at which that substance will melt. It's always going to melt at that temperature. Okay? When we reach that temperature, it's not going to change temperature until the melting is completed. And that's what we'll see with this guy here. So this is a little familiar to what we were talking about last week. If you have your solid here in this state, okay, and we are adding energy to it, if we are increasing the heat, when it goes from a solid up to this liquid, it's going to reach this flat plane here. What this flat plane represents is the melting point. Okay, that's the point it's going to take to change from this crystal or this structure, that solid structure, into the liquid structure. The same thing is going to be true when you go from a liquid to your gas state. Okay, you're going to have another flat line. That line is known as the vaporization point or evaporation point or boiling point. Those are all terms that are used to represent the same thing. Okay, so that transition from liquid to a gas. So that's when we're adding heat energy. Energy is being added the entire time, but when it's the time needed for that phase change, the temperature actually remains constant. So we have this horizontal line on temperature that tells us that a phase change is happening. Now, if we take energy away, if we lose energy, basically you just have that same curve, only backwards. Okay, your vaporization point is going to be the same as your condensation point. A transition from a gas back into a liquid or condensation, right? When you have your liquid and it's being turned back into a solid, when we are starting to lose more energy, that of course is going to be your freezing point. So think about it, guys. What's the freezing point of water? 0 degrees Celsius. What's the melting point of water? 0 degrees Celsius. Same thing. Okay. When we're talking about those pure substances, all of those pure substances have their own distinct melting point, freezing point, condensation point, but they will all have the same general shape. Okay. The temperature ranges are going to be a little bit different, but they're also going to have the same idea of we have increase, flat line, increase, flat line, increase. Okay, and we can actually use that information to identify what material we have. So if you take a look at this, do you notice we have the increased flat line, increased flat line? All of these graphs have the same general shape. Now some of them are going to stay liquid for a longer time than others. If you take a look at this green one, this is tin right here. Tin will stay in liquid phase for a while before transitioning into gas. It doesn't stay solid, it melts very easily. That's one of the reasons we use it for some of the labs that we do. Okay. Whereas iron, as you can see, will stay solid for a very long time. Okay. Now steel is right here. Do those look the same? Well, yeah. Should they look the same? Well, probably, because steel is an iron alloy. So when we have mixtures, things are going to look a little different. Matter of fact, they sort of look like this. Okay, that's what we're going to do with our next lesson. So we'll come back to that, and we'll try and determine this on our own. All right, have a good afternoon.